Hello and welcome to another video. In this one we're looking at section 5.1 and this is going to be on simplifying and adding and subtracting radicals. So we're going to start by simplifying. We're going to look at what makes something a like radical. Then we are going to actually practice some simplifying. This is going to be review from Math 10. Then we are going to compare and order some radicals. And then we are going to do some adding and subtracting, do some examples of those, and then the last thing we're going to look at is restrictions on radicals. So let's scroll back to the top. So first we're going to start with a definition of what like radicals are, and all like radicals are, as you can kind of see here, they are going to have the same radicand, that is the piece inside the square root, and they are also going to have the same index. So if it is a square root, this one would also have to be a square root for them to be like. If it's a cube root, the other one would also have to be a cube root. So let's write out what a like radical is. They have the same radicand and index. And just to review, if we had some radical here, and we had an n there, and maybe we have an a there, the index is the a, and the radicand is the thing inside the root. So looking at these examples of like radicals, we can see if it's a square root, the other one also has to be a square root, and they both have the same radicand. They're both 7s. This one both square roots, and they both have a 5. This one's now a cube root and a 6x inside. This one's also a cube root and a 6x inside. So those two are the same. The number in front is the one thing that doesn't matter. So like this one, a 5 and a 2, those can be different. Now for not like radicals, that's anything where the radicand, like the 5 and the 3, are not alike, or if the index is not the same. Like this is a square root and this one is a cube root. So those aren't alike. So the next thing we're going to look at, just below there, it says determine whether the following are like radicals. So in this first one, the radical there is root xy, and in the second one, we have root yx. So all they've done is they've changed the order of this x and y, and that is okay, that is fine. It is still a like radical, because if I took that 3 root yx, and I can change the order of multiplication, okay, that doesn't change anything. And now I can see that is the exact same as what this is. So those are like radicals. So we're going to say yes for that one. For the next one, we got square root 2, and then the second one has a square root 3. So those ones don't have the same radicand, so that one's going to be a no. And then the last one, we got square root of 2 for square root 2, and then we got square root 8. Now with that one, they don't look the same either. Okay, so I'm going to put no, but sometimes we can actually simplify to get them to be like radicals. So this one we can actually simplify, and we're going to see how we can do that in this next part, but for right now, it is not a like radical. So moving into this simplifying section here, this is review from what you should have done in a previous math course. So the first example, we got root 8. Now, whenever you guys have a square root, what you want to do is you want to try to break down the number into numbers that are perfect squares, because it was a square root. So I want to try to break it down into numbers that are perfect squares. Some perfect squares I'm just going to write up top here. So those are all perfect squares, and if you have trouble remembering perfect squares, I'll show you a way that we can find those. So if we took 1 and we squared it, that's going to give us a perfect square. So 1 is actually a perfect square. I didn't write it here first because it's not going to be useful for simplifying. Then I could take 2 and square it, so I know 4 is a perfect square. I could do 3 squared, so I know 9 is a perfect square, and you could just keep continuing this. So that's just a way to find out some of your perfect squares, or you can just memorize some of them. So we're going to break down the 8 into one of those perfect squares, okay, and I have a 4 there, so I'm going to break it down into 4 times a 2. Now the first one, I'm going to do it kind of slower, And then after that, we're going to go a little faster. So square root 8, I could change into 4 times 2. Okay, and then with radical rules, what we can do is we can break apart the radical so that it is root 4 times root 2. And then the square root of 4 is just equal to 2. So really what I have here is 2, that's from this one, times square root 2. So I can write 2 times square root 2, and you don't have to put the multiplication sign in between. You can just put 2 square root 2. So for the next one here, we want to try to break that down into some perfect squares. So I know 100 is a perfect square. That's 10 squared. And 100 times 2 gives me 200. And then what I'm going to do a little shortcut here where I take the square root of it right here. So the square root of 100 is 10. So I know a 10 is going to be able to come out. And this 2 here is stuck back inside the radical. So what I get is I got that 3 out front times, and then this 10 got pulled out. So 3 times 10, you always multiply. So 3 times 10, and then we still had that square root 2. And then I can simplify that. 3 times 10 in front there, that's just 30. So I got 30 square root 2. Now another good thing about radicals is that you can check all of these with your calculator. So if you had 3 square root 200, so 3 square root of 200, let's see what that gives us. So we get this decimal here. Now I can plug in what I just reduced it to, and I should get the same thing. If I don't get the same thing, that tells me that I didn't simplify it correctly. Okay, and I do in fact get the same decimal, so I know these two are equivalent, so I know I got that one correct. Looking at number 3 there, this one now has a variable. Now this one's a little bit different. So what you want to do is you want to break down that c to the power of 9 into something where the power is going to be a 4. I could break it down into c to the power of 4 times c to the power of 4 times a c to the power of 1. Our exponent rules, you just go 4 plus 1. That gives me 9. So I haven't really changed anything. So I'm just going to rewrite this now. So I got c to the power of 4 times c to the power of 4 times c to the power of 1. And I'm going to put that all in my fourth root. Make sure you don't forget the index. Okay, and then I'm going to break apart each of these so that they have their own radical. So I'm going to have c to the power of 4 in a fourth root. Then I had times by another one of these, c to the power of 4 in a fourth root, times by c to the power of 1 in a fourth root. So c to the power of 4 in a fourth root, those are going to cancel out, so you're just going to get out a c, and same with this one. So each of those, you're just going to get out a c, and a c times a c is just a c squared. So we got c squared times a c in a fourth root. Now there is a quicker way that we could have done this, and you'll kind of learn this as you start to do more of these. What you could do, rather than breaking it into powers of 4, you could break it into a power that is a multiple of 4, and that'll be a lot quicker. So I could have broke the c to the power of 9, I could have broke that down into c to the power of 8 times a c to the power of 1. And then if you take the fourth root of c to the power of 8, you just go 8 divided by 4, and that gives you 2. Okay, so this would have gave us c to the power of 2, and then this other c is still stuck in the fourth root, so you'd get that, and that is the same answer as what we had over here. So this is just another way that you can do it. It'll make it a little bit quicker. So looking at number 4 now, this one is a square root here. So we want to break things down into perfect squares. So 48, I could break that down into, say, 16 times 3. And then the square root of 16, that's going to give me a 4. So 4 is going to come out. And then that 3 is still stuck inside. So 4 is going to come out, and a 3 is still going to be inside. I'm going to leave some space here. The y to the power of 5, I want to break that down into y to the power of 4 and y to the power of 1. Now I chose y to the power of 4 because I know 4 is divisible by what the index is, and the index here is a 2. Okay, so it's a 2. A lot of the time, if it's a 2, they just don't bother writing it. It's just kind of hidden there. So I chose this to be a 4 because 4 is divisible by 2. And 4 divided by 2 is 2. So I'm going to have a y to the power of 2 come out. And then this one is still going to be stuck inside. So I'm going to have a y to the power of 1, but you don't have to put the 1. So hopefully this sounded kind of familiar and that didn't seem all new. These next ones here, 5, 6, 7, if you want to try those first on your own, you can try those. So simplifying the number 5 here, root 52, I can break 52 down into some perfect squares. I'll break that down into 4 times 13, and then the square root of 4 is a 2. So a 2 is going to be able to come out, but the 13, that is not a perfect square. That just gets stuck back in the radical. So we got 2 root 13. Number 6, we have the cube root of m to the power of 8. Now remember, if this is a cube root, you want to try to break this m to the power of 8 down into numbers that have a power of something that is a multiple of 3. So I'm going to break this down into m to the power of 6 and m to the power of 2. 2 plus 6 is 8. And then 6 divided by 3 is 2. So I'm going to have an m to the power of 2 is going to come out. And then this one is still stuck inside. So I got an m squared inside the cube root. Now with number 7 here, we got numbers and we got variables. So 63, again, this is a square root. So I want to break it down into perfect squares. I could break that down into 9 times 7. And then the square root of 9 is a 3. So a 3 is going to be able to come out. And then with this n to the power of 7, I want to break that down into something that's divisible by 2. So I could break it down into n to the power of 6 times n to the power of 1. And then 6 divided by 2 is going to be equal to 3. So I got an n cubed coming out. And this n to the power of 1 is going to be stuck inside. So I'm just going to circle the things that are going to be stuck back in the radical. So the 7 and the n. And then the p to the power of 4, that one is already raised to a power that is divisible by 2. So 4 divided by 2 is 2. So I can put p to the power of 2 out front. And then I'm going to put my square root. And the 7 was stuck in there, and the n to the power of 1 was stuck in there. So the next thing we're looking at is comparing and ordering radicals. So it says radicals can be compared and ordered by converting to entire radicals. And an entire radical just means there's no coefficient in front. Like this one has a coefficient and then the radical. This one is entirely a radical. There's no number in front. So if I convert it all to an entire radical, I can compare things. So if I give you like root 5 and root 6, you can see that root 6 is bigger than root 5. Okay, so we are going to take these down here and we are going to convert them to entire. So 3 root 3, we'll start with that one. In order to convert this to entire, we're going to bring that in, and when we do, because this is a square root, we need to square it. So 3 is going to be brought inside and it's going to get squared, and then we times by the number that's inside. So we have that, and then 3 squared times 3 is going to give me 27. So I have root 27. For the next one there, 2 root 6, it's going to be the same process. When we bring in the 2, we're going to have to square it. So I got 2 squared times by 6, all in the square root. And 2 squared times 6 is 24, so I have the square root of 24. And then root 23, that one's already done. That's already an entire radical. 5, this one's a little tricky because you don't even see a radical. So with 5, you could have 5 times the square root of 1, because square root of 1 is 1. So that's still the same thing. And then when I bring in the 5, you're going to square that. So I'm going to have 5 squared times 1 in the square root. And 5 squared times 1 is just equal to 25. And then just checking this, the square root of 25 is 5. So that one's good. So now we're going to range it from least to greatest. So that's smallest to biggest. So 23 is the smallest, then 24, then 25, then 27. So that is going to be our order. So I'm going to write that. We got root 23, then we had root 24, root 25, and then root 27. Okay, now when you give your final answer, make sure you write your answer using the original numbers given to you. So I want to rewrite this. Root 23 was the original number, so that can stay. Root 24 though, that was actually 2 root 6. So I'm going to change that into 2 root 6. So I have that. Root 25, that was just 5. And then root 27, that was the 3 square root 3. So there it is. They're all in order, and we're using the original numbers. So I'm just going to make a note here, must use original numbers. And I'm also going to mention another way that you could check this. You could take all of these numbers that you got and change those into decimals and then compare and see if it's going from least to greatest. But you cannot use that as a method to arrange it from least to greatest, okay? You won't get any marks on a quiz or a test. You need to convert it into an entire and then compare them. So we're done comparing and ordering. The next thing we're looking at is adding and subtracting radicals. So it says only like radicals can be added or subtracted. And to add or subtract like radicals, you are going to keep the radicand and then add or subtract the coefficient. So an example of that would be like this. We got a root 2 and a root 2. So here we have 3 root 2's and then we add 5 root 2's. So total I have 3 plus 5. We have 8 root 2's. Okay? What you do not do is you do not add the 2 coefficients and get 8 and add the radicand. 2 plus 2, you get 4. You do not do that. Okay? That is wrong. So the radicand inside there, it stays the exact same. It's kind of like when you've done some adding with polynomials. Maybe you had 2x plus, say, 3x. Total, you have 5 x's. You don't have 5x squared or something like that. You just have 5 x's. Okay, so we're going to do some examples here where we are going to simplify the radicals and then combine like terms, so add or subtract them. So in the first one, I have a square root 3. And I have another square root 3, so those two I'm going to write right beside each other. So I got 2 square root 3 plus a 6 square root 3. And then those square root 2's, I can put those beside each other. 4 square root 2 plus square root 2. Okay, and then these two I can put together because they're like, they're both square root 3. So 2 plus 6 is going to give me 8 square root 3. And then with the second two, they're both square root 2's. So I got minus 4 plus there's a hidden 1. So minus 4 plus 1, that's just minus 3 square root 2's. So that one I didn't need to even simplify anything off the start. I could just add right away. Now with number 2, none of these look like. I got a 27, a root 5, a root 80, and a root 12. So none of them are the same, so I'm going to have to simplify first. So 27 I'm going to break down into 9 times 3. And the square root of a 9 is a 3. So a 3 is going to be able to come out. So I'm going to write that. I'm going to have negative 3. And then there was the 3 still stuck inside. With the next one, square root 5, you can't simplify square root 5 down. You can't break it down. So I'm going to have just a plus 3 square root 5. For the 80, I can break that down. And you can break that down into 16 times 5. And then the square root of 16 is just a 4. So I'm going to have minus 4, and then the square root 5 is inside. So minus 4, square root 5. And then the last one, 12, I can break that down into 4 times 3. And then the square root of 4 is a 2. And then remember, we got to multiply, so 2 times 2. I'm going to have minus 2 times 2 is 4. And then the 3, again, that was this 3 here. That's going to be just stuck inside the radical still. So I can see the root 3's I can put together. This one and this one. So minus 3 root 3 minus 4 root 3, that's minus 7 root 3. And then the other two there, I got 3 root 5 minus 4 root 5, that's going to be minus 1 root 5. Remember, just subtract the coefficients in front. 3 minus 4, we get negative 1. On to number 3 here now. So this one's got some fractions, and note this one is cube roots. So we want to break it down into perfect cubes. So the cube root of 27, that actually is a perfect cube. That's just equal to 3. So I'm going to have 3 times a quarter. So that's going to give me 3 quarters. Just going to write that on the right there. Then with the next one, the cube root of 16, we got to break that one down. So I know some perfect cubes. I'm just going to write those on the left here. The first one is 8. That's 2 times 2 times 2, 2 cubed. Then the next one is going to be 3 times 3 times 3, 27. And then 4 times 4 times 4 is 64. And then you could keep going up and up and up, but we're just going to put the first few there. So 16 I could break into an 8 times 2, and then breaking down the 8, the cube root of 8 is 2. So I'm going to have 2 times a half. That's just going to equal 1. So I got a 1 for that. And then the 2 there, that is still stuck inside the cube root. So I got the cube root of 2. Looking at the next one, the cube root of 64, that one is a perfect cube. That just equals 4. So I got 4 times negative 1/3, that's going to equal negative 4/3. And then the last one, 54, I want to break that down. 27 is a perfect cube, so I'm going to go 27 times 2. And then the cube root of 27 is equal to 3. So a 3 will come out, and 3 times 1/5 is just equal to 3/5. And then I still have this 2 inside, so I have the cube root of 2. So now that I have that, I'm going to add my 2 square roots together, and I'm going to add my other 2 numbers here together. All of these, like these two, they're going to need a common denominator, so I'm going to do that in this step. So with the 4 and the 3, a common denominator for those two is going to be 12. So I'm going to multiply by 3 with this one, 3 with that one, 4 with this, 4 with this. And then I'm going to write those out. So 3 times 3 in that first one is 9 over 12. And then the second one, 4 times 4, we got 16 over 12. So I'm going to be able to add those now. These other 2 ones up here, we got to find a common denominator with those. This one's going to be a little bit easier because this number here is just a 1. So a 1 I could change into 5 over 5. So I'm going to do that when I get to the next step here. So I'm changing that 1. So I got 5 over 5 times the cube root of 2 plus 3 over 5 times the cube root of 2. So adding these first 2 together, remember just add or subtract the numerators. So 9 minus 16 is going to give me negative 7. So I get negative 7 over 12. And then with the last 2 there, I have, for sure it's going to be positive. And then 5 plus a 3 is going to give me 8. So I got 8 over 5 times the cube root of 2. So last one here, number 4. These are both square roots, so they got hidden indexes of 2 in there. So I want to break them down into perfect squares. So 20 I could break down into 4 times 5. And then the square root of 4 is 2. And then this 5 is still going to be stuck inside. So I'm just going to write that out. I brought out the 2. And then there was a 5 still stuck inside. And there's also that x stuck inside. So I got root of 5x. And then I have minus, and then with the second one, 45, I want to break that down into some perfect squares, so I can break that down into 9 times 5. Square root of 9 is a 3, and then I can do 3 times 3 there in front. That's going to equal 9, so a 9 is brought out. This 5 is still stuck inside, and this x is still stuck inside. So I got 5 and x inside the square root. Now, a good hint with a lot of the questions you guys do, they're kind of designed so that you're going to get out like radicals at the end so that you can add or subtract them. It might not always happen, so don't force it to be the same, but usually they're going to have something kind of similar and you can do some adding or subtracting. So last step here, I can do 2 minus 9. That's just equal to -7. And then remember the radicand stays the same. So root 5x stays the same. So now that we're done those, we can move to the last thing we're going to look at, and that is going to be dealing with restrictions. So a restriction, if you think about the word restriction, that is something that's going to stop or not allow you to do something. So in everyday life, we even have restrictions. If you were going down the road, right, you're most likely going to see a speed limit sign, and that is like a restriction. It says you have to be below a certain speed. It's kind of the same for radicals. So with radicals, if you have something inside of a radical where the index is even, so like this one has a index of 2, then whatever is inside there, it has to be non-negative. So that's what this first line here is saying. If the index is even, then it has to have a non-negative radicand. If it has a odd number for the index, then the radicand can be any real number. So there's no restrictions on those. So it's kind of like a road where there's no speed limit. So if you ever forget these two kind of properties, I can show you how you can double check with a calculator. You could go into your calculator and try to put in, say, -4 in a square root, and you're going to get an error. Okay, now if you put in, say, a 0 in a square root, that's going to be allowed. Square root of 0 is 0, and anything positive, you could check it, it's also allowed. But as soon as you put in something negative, you're going to get out an error. So whatever's inside there, it has to be positive. But if it is something where the index is not a 2, maybe it's a cube root. So if I put in the cube root of something, I'm just going to go down to the cube root, and let's put in, say, -6, and it can calculate it. So it doesn't matter if it's positive or negative if it is a odd index. So looking at number 1, we're going to have to do some restrictions because it has an even index there. So we have to say 5x, remember it has to be non-negative, so it has to be greater than or equal to 0. And then that's like a little equation that you're going to solve. So to get x by itself, you're going to divide on both sides by 5. 5's will cancel, and so you get x is greater than or equal to, and 0 divided by 5 is 0. So that would be the restriction for that one. For number 2, the index is also even. It's a 2, so we have to restrict it. We got to say whatever's inside there, 2x plus 1, has to be greater than or equal to 0. So to get the x by itself, we're first going to have to subtract 1 from both sides. Those 1's cancel, and I get 2x is greater than or equal to -1, and then divide both sides by 2. The 2's will cancel, and I get x is greater than or equal to -1/2. Looking at number 3 here, the index on this one is odd. So remember we had said up top, if that is odd, then there are no restrictions. And lastly here, number 4, now the index is a 2, so that's even, so we're going to have to take the radicand, 5x minus 2, and this has to be positive, so it's got to be greater than or equal to 0. Add 2 onto both sides, so we get 5x is greater than or equal to 2, and then divide both sides by a 5, so we're going to get x is greater than or equal to 2/5. So that was our last practice example for our restrictions. At the bottom here now, I'm just going to write out our textbook questions. And one final note here, for questions 5 to 10, you're just doing parts B and D.